진조. Okay, so I think it's time to start. So please take a seat. So today, it's our great pleasure to invite Professor Tomo from National Tsinghua University. Please take a seat. So, we dance. So, congratulations. Okay. And then, before starting, so let me briefly introduce Professor Goto's career. He got a PhD degree from University of Tokyo, and then after some fellowships, including Johns Hopkins University, and then University of Hawaii, and also University of Copenhagen. And then after these fellowships, actually he got an assistant professor position at National Tsinghua University. Now he is promoted as a full professor at Tsinghua. And then also let me emphasize that he was recently nominated as top 2% scientist, who are selected by Stanford University in the US in 2021 and 2022, probably in 2023 too. So anyway, it's a great pleasure to invite him. So let's welcome him.
Thank you very much. Thank you all for coming. It's my great pleasure to visit here at National Johnson University because we have many friends here. Tetsuya-san is my old friend, and then also I actually work with many students and postdocs in Johnson University, including Tetsuya-san, and then Shotaro-san, Yuri-san, John, and Kaiju, and some other students in Johnson University. So we usually, from the Corona period, we usually have a telecom over the internet, but it's actually a great pleasure to visit here and then see them in person. So thank you very much for inviting me. So first I want to thank today, I'm going to introduce these 4 students' works, so these 4 student papers. Then I want to thank, but this is not just these 4 students, but this is collaboration work of many students here at Johnson University and Tsinghua University. So I want to thank all the collaborators at the video. Okay, let's get started. First, I want to explain maybe how many of outside of astronomy, how many of you are not in astronomy field? Okay, so most of you are in astronomy? Okay. So first I want to explain a little bit what we astronomers are doing. Okay, then, say, if you wake up in one day and then you are in the middle of the ocean on a boat, and the only thing you can see is the ocean, and you are alone, then what do you think? What do you want to know? In this case, but in the next slide, it's a reality. So if I were alone, Yuan, what do you think if you're here? This is you. So what do you want to know? Yes, thank you. Yeah. So thank you, Yuan. So if you are alone and suddenly in the middle of the ocean, probably you wonder, where did I come from? And then where am I going? And then where am I? Right? You wonder, right? Why am I suddenly in the middle of the ocean? Well, of course, we're not in the middle of the ocean. We're in Johnson University, but in the vast space of the universe, we are actually alone on the Earth, right? Like this. So the situation is not like this, but it's like this. So we are in the very large universe. We're on the planet, yeah, like these people are like this, right? And then we are alone on the Earth. Of course, we have ourselves, but we have never seen aliens. We have never seen, other people from other planets, right? So we are alone And we have never seen other place than the Earth, right? We have never seen other alien planets, right? So we are alone in the universe. So similar to the situation like this. So, as one of the astronomers, some of the astronomers wondering, where did we come from? Why are we on the Earth? And then what's going to be our future? So, some of the astronomers, I'm one of the astronomers, who are trying to understand this. So, in other words, we want to review the history of the universe. And in my case, particular, I'm interested in the star formation history of the universe. So when the universe made a lot of stars, like the sun, and then what's going to happen in the future? That's one of my scientific interests. Okay, so let's get started. By the way, this person ran Taipei Marathon 2 years ago, and then he said he found a new universe. So that's maybe one way to find it.
That's a confidential picture.
Really, it was on someone's Facebook. So okay. Okay. Then in this talk, there are two important key points. So there'll be exam later. So this will be in the exam. So please remember. So the first one is NASA's new James Webb Space Telescope. And the second one is infrared light. Let's start with NASA's James Webb Space Telescope. So, James Webb Space Telescope is this. Ta-da! My student made it. So this is NASA's new space telescope. And then, I hope you can see how big this is. So you see, this is a mirror of the telescope in this part. And then this is the size of the people. So the mirror, this diameter is 6.5 meters. So it's probably about the size of this classroom. So this is the first of the next generation telescopes. And then, maybe compare with previous telescope, you can see it's big, right? And then this is even compared with Hubble Space Telescope. Maybe Hubble Space Telescope is very famous, right? Hubble was 2.4 meters, and James Webb is 6.5 meters. So even compared with Hubble, almost 3 times larger mirrors. And this is actually going to bring a revolution to astronomy. So now is a very good time to do astronomy. And James Webb Space Telescope is actually infrared telescope. Hubble was optical telescope. James Webb is infrared telescope. And compared to NASA's previous Spitzer infrared telescope, it's almost 10 times larger diameter. So that's the source of the revolution. And then if you compare the sensitivity, so James Webb Space Telescope, JWST sensitivity is here. So this is wavelength and sensitivity, and the smaller number means better, right? And then compared to previous Spitzer telescope, which UN is the next part of Spitzer, but UN, JWST is 100 times more sensitive. So there's a chance to do 100 times better work than UN. 100 times is going to bring us revolution. So, do you know who this is? John, do you know who this is? Tetsuya-san?
Galileo.
Yes, exactly. So Galileo Galilei. So Galileo Galilei made the first telescope humankind had, and then he discovered 4 satellites of Jupiter, right? And then this first telescope was actually sensitivity was 100 times better than human eyes. And then, if you know, this telescope brought a lot of new discoveries to us, and then that is going to happen with this new JWST telescope. Okay, maybe it's easier to show than speaking. Seeing is believing, right? So rather I explain, it's better to show you a picture. So this is previous Spitzer telescope. This is 85 centimeter mirror, so the mirror was about this size. And then this is the power of 6.5 millimeter. And you can tell, right? those bright stars, Spitzer telescope can see, but many, many numerous faint objects Spitzer cannot see, JWST can see, right? This is the power of the 6.5 meter telescope. Okay, I actually even made a video, even compared with Hubble Space Telescope. Yes? Even compared with Hubble Space Telescope, you can probably see more objects here with the JWST image than compared with the Hubble Space Telescope. Because JWST is 6.5 meter, 3 times larger mirror, so the resolution is also 3 times better. Okay. I actually have the music here too, so maybe if you're online, you can hear the music probably. And then, so that's first point. And then next point is we're using infrared light. That's the next key point. And then, okay, suddenly we're gonna play rock, paper, scissors, okay? So can I borrow your hands? Please raise your hand. Okay, we're gonna play rock, paper, scissors. Yes. Your cell phone, please put your cell phone and then raise your hand. Okay, rock, paper, scissors. Okay, who has scissors? About 1/3 of people, right? You guys won, okay? Because the answer here is here has a paper. Only 30% of you won because you only have optical eye. If you have infrared eye, you can see through the dust. Well, this is dust, right? This is garbage, plastic bag, so it's dust. And then if you have infrared eye, you can see through, so you can see what he has. So that's important. Infrared light can bring more information than optical. That's the point I want to make here. This is also true in the universe. So this is optical picture of merging galaxy or merging galaxy. So those two galaxies are merging, right? And then this is a zoom in at the center. And then you see nothing in the center, right? In optical light. But if you use infrared light with JWST, this happens there. There's a very luminous source. This source is 100 times brighter than the other part of the galaxy at the center. I should say 100 times more energy is here than the whole galaxy at the center. And then you'll miss it if you are using optical light. So that's why infrared light, you need to see the hidden thing, to see hidden power. Infrared light is important. And even the Little Prince, you know, the fairy tale story, Little Prince, have a famous quote. One sees clearly only with the infrared. Anything essential is invisible to the eyes. So they knew that in 19th century already. Okay. This is another example in the universe. So this is a picture of dark nebula. So obviously, central part is dark, right? What's happening here? There are no stars here? It's not true, because this is optical light. You don't see stars, but if you use infrared light, you actually see stars inside. Okay. Then, so I said I'm interested in star formation. So if you want to see star formation, infrared is particularly important because these are the newly born stars. And then as you can see, newborn stars are surrounded by dust because new stars are made from gas and dust. So gas and dust in the universe, they collapse with gravity, and then they are made to create a new stars. So stars are born in dusty area. So if you want to investigate dusty area, infrared light is very important. Okay, if you look at the background light of the universe, so if you look at the sky, where nothing, you see empty. And then see how much light is coming in optical, how much light is coming in infrared. Half the light, this part, is coming from infrared. So this is optical part, and this is infrared part. And so half of the energy of the universe is coming in infrared. So that's another importance of using infrared. So that's why I talk about a little bit of history. That's why we made and then use this Akari Space Infrared Telescope. But infrared light, the Earth's atmosphere is very bright in infrared, so we need a space telescope to observe infrared. So that's why we made a space telescope and then launched it. By the way, this is Akari Space Telescope. I also have a space telescope here. So that is before I came to Taiwan. So this is the Akari Space Telescope inside here. Then we launched with Japanese M5 rocket. Here, its telescope is here. And this, by the way, this mirror is 65 centimeters. So actually, this database is 10 times larger. This doesn't scale. Okay. Then the purpose. Okay. There's a launch movie. I have sound here too. This might create echo. So that's the launch of the space telescope. And then Akari made observations like this. It was looking outside of the Earth, the opposite direction from the Earth, in sun-synchronous orbit. And then, yes, the purpose is to see through dust to investigate star formation. And this is my earlier work, not this work. But so before I investigate something called luminosity function. Luminosity function is, this is the luminosity, brightness of infrared galaxies, individual galaxies. And then this is number density, so how many of them are out there. And then you can see, earlier in the universe, there are more galaxies, more infrared galaxies. And if you integrate this, you can reveal the cosmic star formation history of the universe. So the x-axis is redshift. So as you go back in the past in the universe, then there are more. This is star formation rate in infrared. So there are more and more stars are created in the past. So that's the history of the universe. So for example, at redshift 1, that is 6 billion years ago, the universe was creating about 10 times more stars 6 billion years ago. That's the history of star formation history of the universe from this telescope. But this is small telescope, 65 centimeters, so it had a limitation. It's only going to here, redshift 1.5, so it's only going to something like 10 giga years, 10 billion years ago, not much farther back in the universe. And also, it was only detecting very luminous infrared galaxies only. The no faint galaxies detected because it was 65 centimeters. So now, and then we are actually planning to build the next space telescope, infrared space telescope called Spiker, which is 3 meters, so that's much larger than that. But some of you know that because of the funding cut, this didn't happen. We didn't have enough funding. But suddenly, last year, NASA created JWST, which is 10 times larger than this Akari Space Infrared Telescope. So it was very unfortunate moment for us because our own next generation telescope was cancelled, but then NASA created JWST. That's really lucky, fortunate for us. Okay. Then what's really nice about us is this telescope, JWST, is, I would always say, 10 times larger Akari. The reason is here. So this is comparing Akari's mid-infrared filters. So these are 2 micron to 24 micron wavelengths on mid-infrared filters. So in these colors, this Akari telescope can take pictures, 2-micron picture, 3-micron picture, 4-micron picture, like that. And then if you look at JWST's filter, it's very similar, right? This is 5 micron to 25 micron, and then it has same number, 9 filters in mid-infrared. So this is very good for us because our analysis technique, we wrote many papers with Akari. All these analysis technique can be directly used for JWST. So that's actually, very straightforward continuation for us. So that was what working for us. And then, in addition, NASA is very generous. I really respect their policy. So a lot of JWST's survey data are publicly available immediately. So when they take data and then release data, there's no private time. They don't keep the data secret. They release the data for worldwide science. So that's a very generous policy. So even we in Taiwan can download the data and then do science with latest database data. Okay, so that's very nice. Okay, and then they started releasing the data last year in July. So so it's like a competition for all the astronomers in the world. It's let it go. No one touches the data in advance. It's from July. So we wanted to do the science with this data. However, at NCHU, we only have the undergrad students, and then they ask me interesting questions. What is PSF? What is magnitude? Is brightness? And then, Tomo-san, I cannot open fits file with Excel. Of course, you need some programming, right? So, what to do? And then we decided to start with number count. Number count is just counting how many galaxies are there as a function of light. So this background is JWST image. So you see many galaxies, right? How many are there? So that's the first step that we decided to take. It's very simple, but it's fundamental statistics, and then as I show you later, still carry important information on galaxy formation and evolution. So we decided to start with this. And then Jimmy, this is one of the students of mine, he actually quickly analyzed, and so these are number counts in 7 micron, 10 micron, 15 micron. The field is this database, is Stefan's quintet field. So there are 5 big galaxies, so that's called Stefan's quintet, but he's not using these galaxies. He's counting these faint galaxies in the background of the Stefan's quintet. And then, as you can see, as you go faint, okay, I have a broad zooming. So let's zoom into one filter. So this is 50 micron number count. So as a function flux, as you go faint, you have less and less galaxies. So it's number of galaxies. And then this, in the brighter part, is result from Akari and Spitzer, including our previous work. And then with JWST, we can probe to much fainter magnitude. And then so these are the JWST data Jimmy measured. And then as you can see, in previous work was we were probing millijansky level. But now with the power of the JWST, we are going to microjansky level. So there's 1,000 times difference between previous telescopes and then JWST because of the power of the 6.5 millimeter. So that's a new work, 1,000 times fainter galaxies we are looking at. And then this Jimmy's paper was actually quick. So the data was released in July, and then he submitted within 1 month, and then his paper was accepted in September last year. So that was very well done. It was quickly accepted, so that was nice. And actually, this was, I believe, it was the first JWST paper in Taiwan, and then probably third or fourth, even in Asia. So well done. Jimmy was actually an undergrad student. He started this. And then another student, Kosas, also did the same thing, number count, in another field, Shear's field. So this background is a little bit different field of JWST data. And then in this field, JWST has more filters. So he did it 7, 10, 12, 15, 18, 21 microns. So there are 6 rounds. And then his paper was accepted this morning. So that was very good timing. So that's why, well actually until this morning I had here, I wrote submitted, but now I had to change accepted because of his paper accepted, but it's a good news. And then let's zoom into one of the filters. So this is 7 micron filter. And then again, as you can see, Spitzer and Akari previous work was probing milli-Jansky level. But now with JWST, we can probe into micro-Jansky level. So that's the 1,000 times increase in the sensitivity. Okay. Then you might be wondering, these are just number counts. What physics are you learning? It's just counting numbers. Anyone can do it, right? You can count numbers, right? 1, 2, 3 galaxies. But what physics are we learning? Maybe you're wondering, anyone can do it, it's boring. But, so the important thing is how do we extract physical information, physics here. And usually, when we have astronomy data, we take this data-driven approach. We measure, when we detect galaxies, we measure distances to these galaxies. And once you measure the distances, you can measure the intrinsic luminosity. And then create the luminosity function. And then by integrating luminosity function, we know the cosmic star formation history. That's a regular approach, data-driven approach. But this is a little bit difficult for undergrad students. So what we did is model-based approach. So we made assumption to fit galaxy number count. This is a little bit maybe detailed, so I'm going to simply explain. If you want to know details, please ask me later. But he assumed, just simply, he assumed the same shape of the luminosity function and then parameterized its evolution using these 4 parameters. Okay? These 4 parameters in the luminosity function. So, then he does that. Well, this part is actually done by postdoc, Song Jin Kim. Yeah. And then he assumes this evolution, parameterized evolution luminosity function for 5 different population of galaxies, representing population of galaxies. So she simplifies universe. Universe is only made of these 5 types of galaxies, and then their evolution follows described by these 4 parameters. Okay, these are AGN, type 1 AGN, type 2 AGN, star burst, star forming galaxies, and composite galaxies if you want to know them. Okay, so now if you simplify the universe like this, you decide those parameters and then you know everything. That's his model. Okay, what I mean by knowing everything? If you decide these 3 parameters, then that means you parameterize luminosity function, right? So these are luminosity functions for 5 different types of galaxies with its evolution. So as a function of luminosity, galaxy number density about like this, and at some point it starts decreasing. So that's his model, right? And then that happens slightly different way for different type of galaxies. So that's his universe, his model universe. If you do that, once you decide parameters, you know all the evolution, right? So you can calculate those galaxies. Look, how does it look like to us? What the brightness and what color? He can calculate that because once he decided those parameters. So with these parameters decided, he actually know the number counts at what kind of flux, how many galaxies you see. I mean, from each redshift, how many galaxies you see. You know the number counts, right? Then, you know what you can do? If you do that, you can fit galaxy number counts, right? So these data points are galaxy number counts we measured. Actually, this course has measured. He's very happy today. From JWST data. You remember, we count the galaxies, right? How many of them, right? So these are these red data. How many? Okay. And then now, this red curve is the best fit to this observation number count. So this is the best fit. So it's in the middle. And then once you fit, you have the best fit parameters for the luminosity function evolution, right? Then you know everything in the world. So then you know that okay. This plot is very good. This is showing how this works. So so those red points are data points from JWST, right? And then as you change those three parameters that he had in a luminosity function, you see the curve, number counts curve in the top plot. The curve is moving, right, as he changes this particularly this parameter. And this is how he's trying to find the best fit parameters. And then this is a cosmic star motion history. So as a function of redshift or time, look back time. So this is present, this is past in the universe. How many stars are created is y-axis. And then this, according to the best fit parameter, this history, star motion history of the universe is changing, right? This is what he is doing. Okay. Then once he decides he finds the best fit parameter, so he knows the cosmic star motion history, which is shown here. So here, the red part is a cosmic star formation history found by the best fit parameters to the JWST number. So by this something. So as you can see, the JWST measure the cosmic star formation history. So this is present, right? So this is the how many stars are created now, and then it peaks somewhere around a little bit before redshift 2. That is something like 7 or 8 gigayears ago, 8 billion years ago. Universe was creating stars 10 times more, and then beyond that, more past from there, 10 gigayears ago, 11 gigayears ago, universe was creating less stars. That's the history of the universe. That this is the goal that we wanted to figure out. And there are 2 points here. 2 important points is okay. So compare the previous one. So those other colors are previous work, including my points from other work. So more or less, it's matching. It agrees with previous work. But there are 2 important differences here that we probe this using previously unseen micro-Jansky sources. So we figure this out using 1,000 times fainter sources. So there's a fundamental difference. Previous work was only using bright sources to figure this out. We are using 3 orders fainter sources, so it's more reliable. And the other point is we're using infrared. So infrared, as you can see, as I showed in the beginning, infrared we're seeing the sources under the dust, hidden by dust. So that's one thing. Okay, so there are 2 advantages of our work, and then also among infrared works, this data point. Okay, so those 2 are important improvements compared to previous one. Okay. Then he also figured out the black hole accretion history, black hole formation history, because when he modeled the universe, he had 3 types of galaxies and then 2 types of black holes. And then so if you just plot the black hole part, it's a black hole accretion history, which is also very interesting. So this red curve again is a black hole accretion history from the best fit parameters. And then here is a present again, and then for example at redshift 2 or so, universe was creating black hole like 2 orders more. So there are 100 times more black hole creation at redshift 2. That is something like 8 gigayears ago, 8 billion years ago. And then what's interesting is this peak is a little bit more past than the star formation history. So star formation history peaks a little bit before redshift 2, right? But then black hole formation is a little bit past redshift 2, right? So maybe, although errors are large, the black hole may have formed, black hole formation peak was maybe before the star forming peak. That's interesting information, implication. Yeah, okay. Well, actually, he plotted here as a ratio, so that's for the earlier maybe. Black hole formed earlier maybe. Okay, so that's his work, Sonji Kim's work. And then in the middle, those works are submitted last fall. So it was very quick work. But in the meantime, this student was so good, Jimmy Lin was so good. So I said the regular data-driven method was difficult. So that's why we took the model-based approach. But he was managed to do this data-driven approach by himself. He's very good. So he measured the distances to measure the individual luminosity and then measure the luminosity function directly. Let me quickly go through that. So by SED fitting, so-called, so these purple points are JWST data points for one galaxy. And then he fit the spectral energy distribution model as a function of observed wavelength. And the best fit one is, I believe, it's a black line. And then by fitting the black line, he also find the redshift, so-called the distance. He can measure the distance. So in this way, by fitting individual galaxies, he measured distances to each galaxy. So he did that for all the galaxies, about 500. And then once so this is measuring distances. So this is the distance he measured, and this is the distance of some part of the galaxy have known distance. So compared, and it's a good y equal x line. So he measured distance is, I think accuracy was something like 5 or 4%. So that was good. And then once he measured distance, if you know the distance, you can calculate intrinsic luminosity, right? Not the apparent luminosity, brightness. So that's what he calculated here. Y-axis is intrinsic luminosity. And of course, if you go to more distant, you can only see the bright sources. So this is the sensitivity limit of the JWST telescope. So he measured the luminosity of individual sources. And then you can do statistics as a function of luminosity, intrinsic luminosity, and how many galaxies are there. So these are luminosity functions at each distance. So nearby and distance, nearby and more distant, more distant. Okay? And if you do that, you integrate this, then you get how many stars are created in the universe. So he measured the cosmic star formation history. It's the same thing, but in his case, he measured the distances and luminosity to individual sources, not just number counts. So that's more sophisticated analysis. And his data points are black. So again, as we go back in time, from the present, universe was around redshift 2 or so, creating 10 times more stars, and then gradually declining towards more in the past. So that, and again, this is first time in infrared star formation history measured with JWST. And then among infrared work, this is going to redshift 4. This is almost like 10 billion years ago. This is the most distant universe's data point measured in infrared. Again, infrared is this important to see through the dust hidden population, right? So that's well done. And his paper is also recently submitted. This is his second paper with JWST. Okay, then I want to change the topic a little bit here, and I want to introduce this poet's another student's work. Her paper is also accepted last week, so she was very happy about that. Then she is trying to find new brown dwarf stars with the JWST data. What are brown dwarf stars? Brown dwarf stars are something between star and then planet. So in this picture, this is Jupiter, right? And then Jupiter is, have you heard that Jupiter is 40% larger? It was a star. Jupiter is not a star, it's a planet, right? Because it doesn't have enough mass, so it cannot create the hydrogen fusion to emit the light. But the brown dwarf is at stars at the limit, so it can create the lightest stars that can create the hydrogen fusion and then emit the light. And that's very interesting because, we want to understand the physics. So you may have heard of the star, the type of stars, O stars, B stars, A stars, F stars, G stars, like sun. This is a temperature sequence, high temperature, lower, 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 and the sun is G type star. And then usually the textbook stops here, M star. But it continues into brown dwarf stars. If you go lower temperatures, you have even lower temperature stars, 3000 degree, 2000 degree, and even 1000 degree. And then if it goes to 200 or 300 degree, that becomes Jupiter. So this part is very interesting, the border between star and planet is something interesting. But these stars are very difficult to be found because these are faint. They are small mass, so much fainter than that, those our sun and regular main sequence stars. So it's difficult to be found. So something like this, something in between stars. Okay, then again, here comes the power of 6.5 meter. Previously, the brown dwarf stars are only found around 20 parsec around our Earth. Because they are faint, we cannot see very far away. It's very faint, so difficult to be seen. But with the power of the JWST, we can find brown dwarf stars as far as 8 kiloparsec, 8,000 parsec. Okay, then then JWST is this near-infrared filter. Infrared filters are also very good to find these kind of stars. Because these type of stars, temperature is so low, about 1000 degree, so the molecules can stay in the atmosphere. And here, particularly, so like ammonia, water, and these kind of methane, these molecules can survive in the atmosphere. For example, our sun is 6,000 degrees, right? So those molecules are destroyed by the heat. So they cannot stay in our sun. There's no, have you heard water in the sun, right? There's no water in the sun. You cannot drink the water in the sun. But in these planets, the atmosphere has water. And then particularly, this water absorption at 2.7 micron is very, very prominent. As you can see, if you go lower temperature, there's big absorption by water molecules. And this is a very good way to find those brown dwarf stars. And then JWST, NASA's people clever, have a filter right at the right exact correct wavelength. So if you want to find those low temperature stars, you just find the object that's very dark in 2.7 micron. That's what my student did. So here, if the object is, so this is plotting 2.7 micron to 4.4 micron color, and if the object is very dark in 2.7 micron, because of the water absorption, the object is going to come in here. And then those green ones are modeled, but then he found that this one point, so there's one star for in this region with diversity. Let's look at what this object. So this is the object, SCP of an object, and then these black points are data from diversity. And as you can see, this 2.7 micron is very faint, right? This is unusual. Usually galaxies like this with similar brightness. This doesn't happen for galaxies or even regular stars. This is very unusual that one data point is very faint. And then that's because this is a ground hole star, low temperature star. According to high CD fitting, temperature is 1300 Kelvin, so that's a very low temperature. The mass is only 5% of the sun, that small star. And then the age is about 2.5 billion years. So it's a little bit younger than sun. And then also distance is 2.5 kiloparsec away. This is the most distant brown dwarf star ever found. She found it thanks to J-based telescope. Okay, so this is how it looks. Does it look like a star? Yes, it does. It's just a point, right? There's no spiral or something, so it looks like a star. And then, okay, we should go a little bit more sophisticated science. Do we expect how many brown dwarf stars we expect in all the database fields? So if we combine all these shear Stefan's printed glass database field, which is 60 square arc minutes, something like that. And if you multiply previously known number density of brown dwarf stars, expected number is 0.16. And then she found one, right? Is that possible? Well, I think it's okay. You know, she needs to be extremely lucky, right? She found one when you expect 0.16. But you know, it's one in, so how many times? 1 in 8. So if you're very lucky, you have 8 lottery and then you can pick one, the prize that sometimes happens. So I think it's not impossible. Or maybe this is already probing a much more distant universe, much more distant place in the Milky Way, right? 1,000 times more distant than previous one. So maybe the number density could be higher there. That's also a possibility. Okay, maybe it's time to wrap up. I have some preliminary works, but I see some of you look tired, so maybe I should stop here. Okay, I summarize here. So I hope I convinced you that JWST is bringing a revolution to astronomy. So very exciting years in astronomy have started. Then 2 students wrote a JWST number count. You might think it's a simple project, but this postdoc made a model fit to illustrate cosmic star formation history. And also, one student also measured the cosmic star formation history. And another student found the most distant brown dwarf star at 2.5 kiloparsec, thanks to the JWST's power. And then, I hope I showed an example, even undergrad students without much astronomy background can do a substantial, interesting work in with JWST. And then they all, afterwards, or they all came to graduate school, so that was a good news. Okay, I stop here. Thank you, everybody. Thank you, Tetsuya-san. Thank you, organizers.
Okay, so thank you very much, Tomo-san, for
Thank you.
very interesting talk. I'm very happy to see that Taiwanese researchers are really using gender diversity data. So I'm really proud of that.
Well, thanks
so,
to you.
no, I didn't do anything, but yeah, thank you very much for a very good talk. So now it's time for Q&A. So do you have any questions? Okay.
Thank you for your speech today. So I have a question about the JWST. You talk about it can obviously drive, but however, we also have a NOLOY type drive. Can we also obviously let those?
So, what are you talking about? Stars?
Well, I mean, it's a DWARF has what NLOY type. Do you know?
So are you talking about brown dwarf stars? Are you talking about stellar sequence? Sorry, I didn't understand the question.
Which slide are you talking about?
Can you say how important about the T drive?
You mean you are talking about this?
Yeah.
So okay, then what's the question?
Why do we need to observe this?
Okay. So
Importance of brown dwarf.
brown dwarf is some border between stars and then planets. And then it has been very difficult to find these. We only have a handful of those now. So that's why we want to investigate this. And then the scientific importance is here. So we want to understand what happens in such a low temperature stars. So for example, atmosphere. What happens to the atmosphere of such low stars? Why molecules are created out there? Then that helps us to build a history of model of how the stars are created, star formation models. And then yes, so in what kind of situation stars are created? So we ought to understand what kind of situation it becomes, the object becomes planet, and what kind of situation object becomes star. What's the criteria to start hydrogen burning? That's what we want to understand.
So this is the data correct has a lot difficult to face.
Yes, so the main difficulty is these stars are very low temperature, only 1000 Kelvin, and these are very faint, and that's why not many are discovered. It's very difficult to discover these because they are very faint. It's difficult to find. So that's why JWST power, collecting power, is important to discover this faint object.
Okay, I realize. Thanks.
Thank you. A good question.
Great. Any other questions? Yes.
Thank you for your great talk.
Thank you.
I want to ask, according to your research,
Right.
star formation history is different from normal galaxies and other black hole formation history. So do you have a good explanation for that? So the peak of the star formation history is different. So do you already have some good explanation for it?
You mean between black hole?
Black hole and galaxies.
Oh,
This
right.
one,
The
this one.
peak is different, right? So
Yes.
the ratio is highest here.
Yes.
Well, I'm an observer, so
Yeah, I know.
I think this is the first step to show this.
Is there any theoretical prediction before, like people can explain this?
Well, naively thinking, the black holes are much smaller mass, 4,000 times smaller mass than the galaxy itself. So the collapse of the black hole is rather quick than galaxy formation. So we sort of expect this, that the peak of the black hole activity may be precede the star formation. Because black hole is much smaller than the galaxy. But if we can, as you say, if you can precisely decide how much time black hole precedes, maybe that helps us to create a black hole and establish potential models.
That's a great result. So maybe I ask another
Yes.
quick question.
Sure.
That it seems the branch of the chance to observe branch of in the current data is like less than 20%. So
Right.
so why did you decide to do this work?
Oh, that's a great question. So I didn't say that to my students very loudly. So like here,
Maybe you
if I-
cannot find anything.
Yeah. So I didn't emphasize this part to my students. I just encourage students, like, if you find it, it's a big discovery. It's a big discovery, and then I didn't say that you have a chance of finding it, 20% chance of.
Yeah, it's not high.
Right. So, but then, so there maybe the better answers too. So this is only using the initial release data. So there is the initial release data, and then database keeps observing. So they release more and more and more data. So if you establish the method and then just keep searching, in one day she will find it. So even maybe not this time, but then she can eventually find it. And then also, this number is a very low temperature stuff, 1000 degrees. But another way is if you increase the temperature, then the star becomes brighter. So it's easier to find. So if it's 2000 degrees, then this number should be larger because you can search more volume in the same data. So that was my plan. If she doesn't find it, maybe we can increase the temperature.
But then you found at first.
She finds something.
Cool. Thank you.
Any other okay, sure.
Oh, thanks. Great talk.
Thank you.
So I have a question about star formation history,
Right.
kind of derived by the data-driven method.
Yes.
You showed a figure showing derived data points on top of a theoretical curves. Yeah, it's Jimmy's work.
Okay.
Yes, this figure.
Okay.
Yes.
Yes.
Thanks. So if I look at the kind of lowest redshift data point
Yes.
on the left,
Yes.
this is actually above the theoretical data point found by your group, so
Right.
Kim 2023.
Yes.
So this is because our Kim paper model that only number count derived data. So maybe number count is missing some kind of galaxy or some infrared galaxy information. That's why. So this data point is more accurate than the number count method you mentioned, right? Because so I wonder why. So my question is, so the lowest data point,
Yes.
our lowest redshift data point is above the theoretical curve
Right.
derived by Kim.
Yes.
So why is it? Why is it kind of, even if you consider the error bar, it is not inconsistent, right?
Right.
So what is the reason, source of this inconsistency?
That's a very good question. There are multiple reasons for this. One thing is this Kim et al. Is assuming the model shape. So it doesn't have too much flexibility to increase, say, for example, it cannot just increase this point. It's all, model shape is assumed, so the flexibility, there's a limitation. I think that may be the reason. Then, so in that sense, if you just look at the individual point, maybe this data-driven method may be more accurate because it's not constrained. Because in this curve, all these points are correlated, right? Because it's part of the one model.
So maybe stupid question, but can you also So you cannot directly fit this curve, but you can do fitting for different luminosity function. So I don't know how, but is it possible to fit the observed data point, 4 data point on this plot by his model? Is it possible?
Yes.
Okay.
But then, if the individual data points are measured, then I think that's better. Because this curve has extra constraints, the freedom is less. But then these individual points, so to this point and this point are not correlated. They are measured individually.
I see.
But in Kimet, it's all together, it's correlated because of the assumption in the model. So in that sense, these individual data measurements are better. Well, because he measured he did the SAD fit into individual galaxies. So there he's obtaining extra information that Kimet didn't consider the distances to each galaxy. So in that sense, I think these data points are superior.
I see. Thank you. Understand.
Okay, so any other question? I think we have still time. So any easy question is okay. Actually, I have one more question.
Please, thank you.
So you mentioned that there are 2 advantages of JWST. One is sensitivity,
Yes.
another is high spatial resolution.
That's right.
So then I think these works are taking this sensitivity advantage.
Right.
And then do you have any plan to use this high resolution advantage to do more work on galaxies or whatever you want? Future plan.
Well, thank you for a very good question. Maybe you know the answer.
Yeah, I don't know. Yeah.
That's what I'm asking. So, well, actually, for something like ground dwarf work, this JWST superior resolution helps us to exclude galaxies because faint galaxies sometimes look like a star, but JWST can tell it's a star or galaxy. But then another student is doing a morphology of infrared galaxies, and he's finding it very interesting. So these are infrared galaxies he selected, and it looks like a very normal, round, regular galaxies. And this is very unusual because in previous work, infrared galaxies, there are a lot of mergers or disturbed morphologies. That's a typical morphology of infrared galaxies. But these are regular, like round. It almost looks like elliptical galaxies. So that's something new in the JWST morphology. So I think it's interesting.
Oh, thank you, Tomo. Oh, actually, yeah, I didn't know this. Oh, thank you very much.
Thank you.
Thank you. Any other questions? Maybe if no, I think it's already one hour plus, so therefore I think it's time to stop. So thank you very much, Tomo-san. Let's thank the
Thank you
speaker.
again.
And then, so after this, so actually we move to 6th floor
Okay.
to take further questions. So therefore, if we have more questions, so please come to 6th floor. And then today this is the end of the seminar. But I have an announcement. Next week, we have one more Japanese professor who is going to talk about his research. So therefore, we have additional one more next week. Same time, same place. So therefore, if you have time, please come to the seminar. So thank you very much. See you next week.
你什么时候知道？所以你觉得这1天未来？